Section 1.8 talks about continuity. Now, the idea of continuity is simple. If you can trace a curve over its entire domain from left to right with a pencil without lifting the pencil off the paper, that function is continuous. So again, if you could trace a graph from left to right over all of its domain with a pencil without lifting your pencil off the paper, that function is continuous. Otherwise, it's not continuous. Anytime you have to lift, or you have no choice but to lift your pen or your pencil off the paper, that means that function is not continuous there. So the definition is fairly simple. Definition says a function is continuous at a number a if the limit as x approaches a equal f of a. So this is saying three things. This says 1, f of a must exist. 2, the limit must exist. And the third condition is that this limit must equal the y value. The limit, if it exists, that means the limit from the left and the right match, and you want the y value to be filled in. So we start with a simple example. Given a graph, given the graph of f, state the intervals on which f is continuous. Well, let's see. If I trace this left to right, I'll notice that when I get to this point, I need to lift my pen off of the paper, and then here I have to lift it up, and here I'm gonna have to lift it up, and here I'm gonna have to lift it up. So I could say f is continuous everywhere except at x equal, I notice at -2 f of a does not exist. At -1 f of a doesn't exist either. At 1 the limit doesn't exist, and at 3 f of a doesn't exist. So here you're doing it visually, but on the long run we're going to have to show this, which is a bit more work than simply stating. Now, couple of theorems. If f and g are continuous at a point a and c is a constant, then the sum of two continuous functions, or the difference or the product, are continuous. If you take a continuous function, multiply it by a number that's continuous, and if you divide two functions that are continuous, the quotient will be continuous provided the denominator at that one point doesn't equal to 0. And this is a giveaway. The following types of functions are continuous at all numbers in their domain. All polynomials are continuous. All rational functions are continuous where they're defined. Root functions are continuous where they're defined, and trig functions are continuous where they're defined. So if a problem says justify, all what you have to do is say this is a rational, this is a root, this is a polynomial. Here's an example. Use the definition of continuity along with the properties of limits to show that a function is continuous at the number a being 4. So this is what they're asking. Show that the limit as x approaches 4 of f of x in this case being 3 plus the square root of x plus 5 equals f of 4. Well, three things, and we should do them in that order. First, we should check if f of 4 exists. F of 4 would be 3 plus the square root of 4 plus 5. F of 4 would be 3 plus square root of 9 is 3. F of 4 is 6. Well, step 1 is done. Now, I'm going to take the limit as x approaches 4 of 3 plus the square root of x plus 5. And if you remember the shortcut for limits, since this is a radical equation, I plug that in. That's a shortcut. And I'll get a 6. So my conclusion, f is continuous I can write that nicer. F is continuous at x equal 4. Why? Since the limit as x approaches 4 of 3 plus the square root of x plus 5 equals 6, which is f of 4, which is the definition. And that's as far as I have to show. Actually, that's the most work I could show. Looking at the next problem. Well, same deal. First I start off, well here I'm trying to find if the limit as x approaches 1 of x squared plus x over 3x plus 1 equal f of 1. We'll start with f of 1 first. F of 1 is 1 plus 1 over 3 plus 1. F of 1 is 2 over 4 1/2. It does exist. Right? Now what? Now I take the limit as x approaches 1 of x squared plus x over 3x plus 1. But this is a rational function. I could apply the shortcut. That will be 1 plus 1 over 3 plus 1, which is 1/2. So the limit equal 1/2. So my conclusion is that f is continuous at x equal 1 since the limit as x approaches 1 of x squared plus x over 3x plus 1 equal 1/2, which is f of 1. Now the problem is asking at that number. This is continuous everywhere. The only part you're looking at is at this number something is happening. How about this problem? How about C? Well, again, they're trying to figure out, does the limit as x approaches 3 of the greatest integer of x equal f of 3? Well, first things first, what's f of 3? Remember, if this is an integer, that would be just the 3. Got it. How about the limit? The limit as x approaches 3 of the greatest integer, plug it in. This is not one of the 4 functions. I can't use the shortcut on that one. Here, how do you find the limit? You're going to take the limit as x approaches 3 from the left. Actually, let's go this way. Easier this way. So I'm going to take the limit as x approaches 3. The way I'm going to do this, I'll take the limit as x approaches 3 from the left. What would that be? Here's 3. That's 2 and that's 4. If I pick any point to the left, say 2.999, isn't the greatest integer will be the largest integer, or the greatest integer less than or equal to 3? So if I don't reach 3, this is going to be always at 2. What's the limit as x approaches 3 from the right? From the right. If I pick any point to the right, isn't that going to shrink it down to 3? So what's our conclusion? F is not continuous at x equal 3 since the limit as x approaches 3 of x does not exist. So again, 3 things I need to do. 1, I need to show that f exists at that point. 2, I have to show the limit exists at that point. And 3, I have to show that the limit and the y value are the same. Here's another problem. why are the following functions not continuous at A? Now, on a test, normally I ask, is the function continuous at A? Sketch a graph. Let's see how that works. Why is it not continuous at -1? Well, let's see how this works. If I take this and I simplify, I could factor a 2 out. This is really 2 over x minus 1 if x doesn't equal to -1, and 1 if x equal -1. Well, the graph of that, I'm gonna shift so I have a vertical asymptote at x equal 1, horizontal y equals 0. If x equals 0, I get a -2. So the graph looks something like this, with one exception. At -1, if I put a -1 there, 2 over -2 is -1. At -1, -1, there's a hole, because x equal -1 is not in the domain. This says if x equal -1, y equal 1. So graphically you could tell easily what's wrong. The limit exists, f of -1 exists, but they're not equal. And when it says y is a function not continuous, you can't say look at a graph. A graph helps for you to see it, but anytime they say or you want to show, you have to do it algebraically. So you start off with, well, again, why are the following not continuous? Well, we know of one definition of continuity, that is the limit as x approaches -1 of f of x equal f of -1. So start with f of -1. F of -1, if x equal -1, y equal 1. That exists. Does the limit exist? Take the limit as x approaches -1 of 2x plus 2 over x squared minus 1. That will be -2 plus 2 over 0. Hey, what does that mean? That means I can manipulate it. This is the one type of problems we get. You factor the top. We dealt with this before. And if I cancel this out, I'll be left with the limit as x approaches -1 of 2 over x minus 1, which is a -1. Got it. The limit exists. So we found f of -1. We found the limit. We say f is not continuous at x equal -1, since the limit as x approaches -1 of f of x equal -1, which doesn't equal to 1, which is f of -1. So the only conclusion, the only work that we show to support our conclusion is showing the definition applies or it doesn't apply. How about this problem? Well, let's do the limit, then do the graph. So I'm trying to figure out at 3 what's going on. Well, let's see. 1. If I take f of 3, well, when x equal 3, y equal 2, that exists. 2. The limit as x approaches 3 of x over x minus 3. I plug that in, what do I get? I get 3 over 0. Do you remember what that means? Does not exist. F is not continuous at x equal 3, since the limit does not exist. Now if you want to sketch a graph of this, that will clarify things. But again, you can never say look at a graph. If I ever ask show or support, you can't say, oh look, the graph is such and such. We have a vertical asymptote at 3, horizontal asymptote at 1 when x equals 0, y equals 0. That's how the graph looks like. And this piece says there's a point when x equals 3, y equals 2. So you could tell the limit doesn't exist because there's an infinite break. Now they're saying, okay, can you fix it? They're saying the following function is not continuous at x equals 1. Define f of 1 to make f continuous. Well, what does that mean? This is actually, we just did that problem. If you think about this, that is 2 into x minus 1 over x minus 1 into x plus 1. So this is 2 over x plus 1. So f of x is 2 over x plus 1, but do you see what you canceled? Provided x does not equal a 1. Let me show you what that means graphically. What that means graphically, I have a vertical asymptote at -1. They're not worried about that. They only want 1. Horizontal asymptote y equals 0. If x equals 0, y equals 2. So we have a graph that looks like this and like this. They're saying the following functions are not continuous at 1. Why is it not continuous at 1? Because we have a hole. When you cancel x minus 1 out, you say, well, put 1 in there. The point 1, 1 is a hole. So at 1 it's not continuous. How do you fix it? Well, you fix it, if it's only a point, you could fix it by simply saying, well, if x equal 1, how do you fill that hole? Let y equal 1. So that's how you define f of 1. You define f of 1 to equal whatever the hole is. If you fill that hole, now it's continuous. Okay, you might not have seen this. Let's do another one just to enforce it. How about this problem? Same deal. This problem is not continuous at 1. Well, if you really think about it, this is x minus 1 into x plus 1 over x minus 1 into x squared plus x plus 1. Those cancel out. So here, if I was to look at this, graphically, the denominator can never be 0. I have a horizontal asymptote at y equals 0. If x equals 0, y equal a 1. Graph starts next to an asymptote and end next to an asymptote. Okay, that's how the graph looks like. Now, keep in mind, f of x equals why does it look like that? That's odd. Okay, no problem. F of x equals x plus 1 over x squared plus x plus 1, provided x does not equal a 1. So this graph has a hole in it, and the hole really exists at, if x equal 1, I'll get 2 over 3. If x equal 1, there's a hole right there. So f is not continuous at that point. So what do? You say, well, let's set f of 1. If x equal 1, let's fill in that gap. Let y equal 2/3. So you can only do this if you're able to cancel one of those. Meaning, if the limit from the left and the right exists, you can fix it. If the limit doesn't exist, you can't fix it.